So I continue from yesterday. Let me remind you, I spent 2 hours talking about these examples of collective dynamics and the aspect of self-organization. The paradigm was environmental averaging, and I was studying the emergent behavior at a discrete level. And the conclusion that I just told you, but I tried to do something, but the conclusion was the following: if there is a global interaction, then we know everything. But if there is no global interaction, which is the more realistic case, then there is some inherent instability, and therefore, I would like to start today to go to large crowd dynamics. So what is the model? The model is very simple. It's given here, and I hope I convince you that despite the simplicity, it covers an enormous spectrum of different scenarios. So in this case, I took a second order model. We have a collection of agents. They are located at points xi. These are their velocities. And the most important thing, this is the communication protocol. We took it in the canonical case to depend just on the distance, but it need not be the case. There is a notion of neighborhood, which is inherent, goes with the unknown communication protocol. And according to Kant, even if we do not see things at the discrete level, we should go to the crowd dynamics. So let's do this. Let's start now, shift and see it as the big crowd. So the starting point for large crowd dynamics is to look at what is called the empirical distribution. We just put dots at all the points with all the velocities, and we would like to see just the distribution. So as I did yesterday, first of all, I will make one slide which covers everything, and then I will get a little bit to the details, not everything, but just to get you the feeling. So the idea is you look at this empirical distribution and you assume, or you prove, or you justify, depending on the framework, that as n tends to infinity, this function, which is a collection of Dirac masses, approaches a limit, which is a function depending on time, on the location, and the velocity. So it becomes a continuum, and this function, in one interpretation, is the probability of having so many agents or particles at time t at location x with specific velocity v. So it is a probabilistic approach, and I already reminded you yesterday that there is some probabilistic aspect to certain interpretation of actual computations. Anyhow, so this is the probability distribution. We take this probability distribution, we take its moments. So when we integrate the probability distribution, we get a density. When we take the first moment, we get a momentum, and they define, therefore, the density and the macroscopic velocity. And the density and the macroscopic velocity or momentum satisfy the macroscopic equations, which are given here. And these are the canonical mass equation and momentum equation that we are familiar with two exceptions. First, on the right, we have some sort which takes into account, some sort of term takes into account the action, this famous phi, the communication protocol. And second, this is sort of a tensor of the pressure, which is mysterious. We have to close it. We don't do it. It's beyond the description here. So here's the alignment term. Here's our favorite communication protocol. This is the stress tensor because we cannot close by taking the moments. And finally, we get the equation that we will study at the macroscopic level. So that's what we are going to do. But before we do that, let's get into the details. So basically what we are going to do, which is of course the paradigm that was not invented for this framework, but it was invented developed over centuries, starting with Boltzmann and so forth. We start with an agent-based model. That's what we have. That's what I discussed in the last couple of years, yesterday, the last 2 hours. So we have an agent-based model which tells us that we have a microscopic velocity vi, and the momentum is balanced by some sort of a force or action. Without getting into details, it's denoted here by fi. Right? In our case, it's an alignment term. We can add to the alignment also the external forcing and so forth. So this is at the lowest level. This is where we are right now. And now we are going to climb On top of that, we will create now a kinetic model. We will get into details of that. And on top of that, and you can see here on the, this is the details. This is sort of an averaging. And then on top of that, we build the hydrodynamic description. And that's what was written before. So this is the standard hierarchy that I would like to dwell a little bit. So the kinetic description. So the idea is that we have a phase space of positions and velocities for the second order equations. These are our equations. Instead of writing the actions, I just write some sort of a general force depending on our agent. And Fn is the empirical distribution function. This captures the self-organized dynamics of interactions, and it's given here. So what we have here is just an integral. If you think of this integral and you implement it for the Dirac masses, you just get the sum. So the sum is replaced by integrals. And then if we can pass to the limit, this usually in the context of Boltzmann equation and under singular kernels is a very delicate matter. In this case, if we are talking about bounded interactions, it can be justified appropriately, at least since this is a measure in the sense of convergence in, say, in the Wasserstein metric. So I push it under the rug because this is a delicate matter and there are volumes on this question about what does it mean to pass to the limit from the empirical distribution to this probability distribution. So it's either deterministic or probabilistic, and we end up with the Liouville equation. And that's what I'm heading. I'm heading towards the Liouville equation for this distribution function f. So let's see how it works out. I will cover now in 1-2 slides for those who are not familiar. I think it's important and I think it's actually educational to be exposed for that for those who are not familiar with the BBGKY hierarchy. So here's the idea. We have this kind of empirical distribution, and there is one critical assumption that this distribution function, which depends of course on n agents, the n agents are indistinguishable. That's the critical element. So they are all the same. No one is preferred. So we can use here any permutation and we get the same empirical distribution. And then it follows what is written here is the Liouville equation, which is nothing else but in a weak formulation of this transport equation, it's the discrete equation that we had before. So what is written here for the distribution function is just the statement that xi dot equals vi and vi dot equals, this is the action we are talking about, and a weak formulation of that, this is the Liouville equation. There is nothing else beyond that. Okay. The question is what we do with this highly parameterized equation, because this equation is for a function f which depends on 2n vector states. So how do we reduce this highly dimensional equation, which involves two things? There is a transport. This is the statement that every agent just being transported by velocity vi, and then when they get together, they do not necessarily collide, but they are influenced. So every agent I is influenced by all the other agents. So how do we reduce this high dimensional equation? The idea is to introduce the marginal distribution. We essentially say the following: since all the agents are the same, let's probe just arbitrary pair, just an arbitrary pair, and ignore the rest. So how do we do that? We just integrate on everything else except the one pair x1 and v1, and let's see this agent with x1 and v1, agent 1 I can call it, and how it behaves relative to the rest. And the rest are of course the agent 2 and so forth. So we integrate on everything else. Everything else is the rest of the space, and we just single out a typical, prototypical agent number 1. And of course you can see when you integrate over them, you create the marginals, all these gradients will disappear except the gradient with respect to the x1, right? So when I integrate, the integrate will annihilate all the gradients. So one has to do it precisely and to follow the details that I'm running a little bit here. Otherwise, it will take the whole hour, and I still have to get to to higher ground. So what happens eventually is that we will be left with one critical term, that is the interaction between the one agent and the two agent. Who is the two agent? A two agent is a sample agent for the rest of the crowd because they are all indistinguishable. So let's take the two agent and let's see their interaction, which is written here. So what we left when we do these marginals, we get something which has to do with the a function which has to do with the one agent and the two agents. And there is a typo here, x1 v1, x2 v2. And now comes a key assumption called the propagation of chaos, which says that when we take this limit, then the behavior of the empirical distribution is actually the product of the two distributions, which reflect the independence, and there are a lot of story there. Again, I shove it out under the rug, but this is the key point. So we replace now the limiting process by the product of the behavior for agent 1 times agent 2, and we will get, by this limiting process, we will get the Liouville equation. And the Liouville equation simply tells us if you take a prototypical agent 1, now you don't see the 1, it will be transported as before, and then it will be interacted, and this is the force of the action of the rest of the crowd on this agent 1. Okay. Fine. I make here some references, for example, the lectures of Gauls, Gallagher, and Saint-Ramon, and so forth, in order to make it complete, or the convergence of expectations of Schnitzman. These are all classical references, so I just thought it's important to put it tag under the BBJKY and so forth. Okay. To summarize, the passage to the limit, as n tends to infinity, we have the empirical distribution, and then from the empirical distribution, from the Liouville equation, we get the so-called Vlasov equation, and it tells us that if we're looking now at the crowd level, at the crowd behavior, the whole ensemble, then the probability of staying a time t with space x with velocity v, well, this probability is being transported, and it is subject to lambda, as you remember, the amplitude, which may now depends on x, and it's subject to this kind of an interaction term. This is a quadratic term for interaction. Let's write it for one more time. And it's actually pretty familiar. So this is, let's say it's me. I'm at point x with velocity v. I have to take into account all my neighbors in the whole space, namely in y, with microscopic velocity w, and they interact with me. And how do I interact? Well, I have to take into account the difference in the velocities. You remember this was the key point in the alignment term. And how much weight do I give to all my neighbors? Well, it depends on the inference function, which could depend on the distance or general communication protocol. So it's just a continuum version of what we have on the discrete case. And if you want, you can even normalize by the degree, and so forth and so on and so forth and so on. Okay, so here's in Cooker-Smale, the degree we remember is 1. And in this model, we just normalize it by the usual notion of degree. And what we have here is just the simple statement: we strive to align to the mean. You remember that there was the elliptic version, and there's a gradient description. Okay, now what happens with the kinetic description? So here I should stop, and there's a lot of analysis because today is the analytic part, but I'm moving forward. I'm skipping over that, and I would like to move now from the kinetic to the hydrodynamic description. As I move to the hydrodynamic description, we expect, in the generic case, we expect that the distribution function will approach a Dirac mass because we expect a consensus. So in some sense, we expect something and then we justify it. But in general, this is not the case that we really have a consensus, a Dirac mass. But if we have a Dirac mass, then we expect that this distribution function will have some amplitude. This is the density times something which goes with the Dirac mass as a function of the velocities. So all the discrete velocities will go towards a limit, which I will denote here by bold U. This is the expectation. How can we realize this expectation? Well, we take the moments. So the first and the second moments will recover precisely these 2 degrees of freedom, the density and the momentum, and that's what we do. And of course, in order to do that, once we take the moments, there is an issue. So once we take the moments, because of the v in front of this term, we will always get at the higher moments, and there is an issue how we close the system. So this is true in all this passage in the standard machinery. For the passage, you owe me 5 minutes, is that correct? Roughly. Okay. So once you take the first and second moment, the zeros and first moment, you will have to involve the second moments. It's unavoidable. And this is not something that can be proved. It's something that has to come from the outside. You have to bring to the room a person like Maxwell, or you have to say something, but that does not exist in this story. So let's see what we have. We get for the zeros moment, we get the momentum equation, the mass equation. For the first moment, we get the momentum equation, which essentially tells us that the first moment is balanced by the rest. And what is the rest? The rest is the alignment term, and we are already familiar with this term. In fact, this is exactly what we expect, right? The alignment tells me the following. If I'm at time t at location x, I have to take into account the rest of the crowd. What is the rest of the crowd at time t? Everyone which at a point y has this velocity. I have to take the difference in the velocities, i.e. the local gradients. I take into account their density, how dense they are. And of course, I have to put a weight. This is the whole game here, the weight, the communication protocol. So this is the alignment term. So it's not a viscosity, but it's an alignment term. This is the action, this is the force that we are discussing. And if there are external forcing or other terms, potentials, it will come there. I ignore that. And then there is the stress tensor, which always exists. What about the stress tensor? Well, if you'll tell me what you expect from F at the limit, I will tell you what the stress tensor is. But I do not want to impose that. So in fact, we have now a system which is not closed, unless you impose something from the outside. And what can you impose? It's the same thing as assuming that you know what the Maxwellian, what is the limiting behavior. For example, if the limiting behavior, which is called Maxwellian, is a Dirac mass, then basically there is no pressure term. Of course, it's not realistic. You have to take into account a more involved things, and it's open.
Isn't it that point where you could try to invoke actual observations?
Okay. Yes, the answer is yes, but I want to tell you something which is quite astonishing if you wait for 2 minutes. So this is a very important point, right? The closure of a kinetic system is a very important point, which cannot be solved unless you bring additional axiomatization into your model, either by empirical ideas, or either you are Maxwell, or you impose something.
But sometimes isn't it a little bit of tautology then? Because you impose something that will yield your expectations, which is, I think,
well, now the question is, if you are Maxwell, is this tautology or this comes from God? So that's a different story. Or you infer something about the physical system. But I'm going to say, this is a delicate point, that without assuming anything and without the closure, nevertheless, I'm interested not at the time-dependent behavior of this equation, but the long-time behavior. And the large time behavior of this system will be independent of the closure. If you bear with me, I will be able, so this is quite striking, independent of the closure, nevertheless, to say something about the system for t tends to infinity. I don't need the closure. Okay. Fine. So I will not take it to be Maxwellian or any special form. I will just leave it as it is. So this is the pressure term. And before, so this is what happens when I give this lecture, not as a spring school, but this is what happens when at least when I gave this lecture. At the beginning, I was inexperienced, and I talked about the whole thing, the agent-based description, the kinetic description, the hydrodynamic description. I wanted to come to the dynamic description, and I found out that I lost half the audience. Somehow, kinetic descriptions is not well received by the audience. So here come to the rescue Sebastian Moch, and he created this beautiful simulation. Maybe some of you have seen that. What you see on the left is the Viksek model that I spoke about yesterday. What you see on the right is the hydrodynamic description, and you definitely see, well, there is something in the kinetic description that captures exactly what we needed. So this is the pointwise the agent-based description of the Vikshek. You remember Vikshek this is a two-dimensional torus. There is no convergence to a consensus because of the noise. However, there are concentration and deconcentration of the birds. And these are the details. And even if you agree that you are not interested in the details, you're just interested in the dynamics of the concentration, right? You want to see essentially the velocities and the densities. Well, here they are. And you can see by the color system here that you get what you want. You just want to understand the dynamics of the ensemble, right? You don't, when you breathe, you don't think Newton, right? Okay, so there is something in this kinetic description which enables you to go to the macroscopic description, and that's what we do, and we do go now to the macroscopic description. So, finally, we get to social hydrodynamics. The first statement about the social hydrodynamics is that smooth solution must flock. So, here's what we do. So, we have this very simple system, well, you know, the mass equation and the momentum equation driven by this alignment term seems to be very innocent, but you know by now that this alignment term is not as innocent, particularly when it's locally supported. So, this statement goes to a original joint work with Changui, who is here, and the statement is that smooth solution must flock. The only thing I'm interested in is what happens for large time. I don't want to study these equations and to do a million things, just the large time behavior, because that's what Kant told me. So we define the fluctuations. In fact, we found the fluctuation at the discrete level, right? So what are the fluctuations? These are the essentially the L2 diameter, the difference between the velocities in different places integrated with the densities. So I will call these the fluctuation. This is the same diameter that I had yesterday. And then we have the alignment term. So let me do it here. It's very simple. So the equation I'm looking at is ut plus u grad u equals an alignment term. So this is the alignment which I denoted by the alignment term which I denote by a sub rho, right? Yes. A complicated term. If you want, you can multiply it in a conservative form in terms of the density. And that's exactly what I'm doing here. I just multiply this equation by u. That's exactly what I did on the same board yesterday, but on the discrete level. If you multiply by u, you get on the left-hand side the rate of change of the energy. And the rate of change of the energy in this case is the same thing as the rate of change of the fluctuation, which is the same argument that I've done yesterday. The transport term disappears, as is usually the case. And what you get on the left-hand side is the inner product between u and a and the alignment term given here. And this term is negative. This is the notion of coercivity that we had yesterday and we had today. And it's precisely equals the term here. And this term is called entropy. It's not new. It appears in all the fluid dynamics. There is one more thing that bothers you, or at least bothers me. What about this lack of closure? What about this lack of closure? So first of all, if we just ignore it, if this is a monokinetic description, then this is exact. And if it's there, well, you just get an inequality, independent of the closure. You get an inequality. Okay, so why I'm so excited? Because everything will follow now from this statement. Because this statement tells me that the rate of change of the fluctuation, here they are, is equal or less equal than the entropy. But when I look at the entropy, there is something very simple. All I have to do is to take this term, here it is. I move it outside the minimal value, and I get the rate of change of the fluctuation is minus something times the fluctuation, and by Gronwell, the fluctuation will go to 0. How simple? I mean, it cannot be simpler. So let's do this. Let's pull outside this term, and what will be the outside, assuming that phi now depends on the distance, and assuming that phi is decreasing. So the worst case scenario is that phi takes the value on the diameter of the initial data times t, because the diameter of the flow can expand linearly in time. And then we get that the rate of change of fluctuation is upper bounded by minus times the entropy times the red quantity, which we had yesterday. I have to put it in red, and the red quantity has to do with the phi operating on the diameter times t. Hence, we do need now phi not to vanish, right? In fact, if phi will have a fat tail, just as we had in the discrete case, then and only then we will get unconditional flocking. This fluctuation will tend to zero, namely all the velocities will go to the limit averaging velocity. And this is true independent of the closure or anything else. It's so simple that you say, and it's so elegant that it raises the following statement: smooth solution must flock. Question number one, well, when do smooth solutions exist? Question number two, just a second, there is a problem here that we want the inference function of the communication protocol to have a fat tail. In particular, we cannot have compact support. So you say, well, let's try something else. It's too simple. Well, you're welcome to do something else. You're really welcome to do something else. Despite the simplicity, it turns out that this is very sharp. But it does not address the main point. My main point yesterday was that I have a collection of agents and they have local interactions, and somehow something emerges on a pattern emerges on large scale. So we have beautiful mathematics, but it doesn't answer my problem. So this is exactly was the situation for two years ago, and I was really bothered by this kind of discrepancy between what we need and what we want.
So, and you are saying a model that describes what you would expect, that there may be a different aggregation behaviors that is not existing.
A model that?
A model that could capture this non-unique flocking case, so that there is a divergence somewhere.
No, it exists. It exists. Once the phi is not, why the phi is compactly supported, then you get a plethora of different behaviors. Yeah, once phi, I mean, all I'm trying to say, I'm trying to follow now the development in the last 5 to 10 years on the mathematical aspects. And I'm saying that we are still at the infancy of this area, because the mathematical descriptions and the mathematical analysis, that's what we're doing today, the analysis. A lot of work was done, but I'm trying to be honest and faithful to show what are the limitations of this analysis and what is needed. So there are many open questions. That's basically, yeah. So before I continue, so there are two issues right now. First, smooth solution must flock. So it raises the question, what about smooth solutions, which is a perfectly honest question, even when phi is global. And second, we have to talk about short-range interactions. So it turns out that the question of existence of smooth solution, even this is not trivial, and you are not surprised. Essentially, what we have here is a non-local version of Navier-Stokes equations. And we know that Navier-Stokes equations, the question of existence is not trivial. And this here, it will be even more complicated, and it will introduce us to some new concept that we were not aware before in the differential equations. So there is a concept that will emerge, not the dynamics will emerge, but there is a new concept that will emerge as we try to penetrate the behavior here. So let's do this. So first, this is our equation. This is the transport, this is the alignment. I completely ignore now the lack of closure, and I would like to see how these two compete. Who wins? Do we have global smooth solution? It's absolutely not trivial. Case in point, if phi, you can think of it to become a picked as a Dirac mass. What you have here is essentially a Navier-Stokes with a density-dependent quantity. And we know that the real Navier-Stokes, the question of unique existence of smooth solution is not trivial. So in fact, we can write the right-hand side as a commutator between an operator. This operator L phi is simply convolution and multiplication by U. So I would like to consider now a whole class of transport equation which is balanced by a commutator between translation invariant operator and multiplication by U. Here it is. And we will do it for bounded phis, because we think about bounded phi. This is the communication protocol. And we can do it even with a singular phi. And now all of a sudden I remember that actually I have to take into account also singular communication kernels, right? So in the case of singular communication kernels, here is an example. Let's call it phi alpha. It's the absolute value of x to the power the dimension plus alpha. Now you get a singular communication kernel. Now the operator L phi is not just simple convolution. It's actually given by the principal value of this difference. That's the way it's being defined. And in this case, what happens is that the operator, the corresponding L phi alpha, is nothing but a fractional power of the minus Laplacian. So it is connected to the statement now that we have a transport equation, the usual transport equation with the fractional Laplacian, and here they are. And then at the limit when alpha equal to 2, formally what we get is the usual Navier-Stokes equations, but with a density dependent, and the number 2 here is important. It's exactly the power. There's a lot of work in recent years about that. I don't want to get into that. It's exactly the power that gives you this commutator form, which is so important. So I would like to address, do we know something about smooth solution? No, it's not me. I mean, many people worked on that, because it turns out to be not trivial. If there is smooth solution, I know to tell you everything about the large time behavior for global phi, but do we have smooth solution? Well, let's summarize this. Let's summarize this as, well, let's see. Okay, let's summarize as the, okay. I'll tell you what is known. What is known is only for 1 and 2D. Unsurprisingly, 3D is not known. And it turns out that in general, you do not get global smooth solution. It depends on the initial configuration. And there's a phenomena of critical threshold. Let's take even the one-dimensional behavior equation. So in the one-dimensional case, which is as simple as possible, a density and a scalar velocity, it turns out that there is a global smooth solution if, and only if, the initial slope of the velocity is not too negative relative to the initial density. So since this is an if and only if, it's essential that you will not get a slope which is too negative. If it's too negative, then the solution breaks down, just like a wave approaching a beach. Okay. It turns out that if you take a singular kernel, this is bounded kernel, if you take a singular kernel in 1D, this is the singular kernel, then we have this kind of equation. We have this kind of equation. Notice here that there is a density which seems to be completely innocent. Well, this equation has global solution independently of the initial data for any alpha between 0 and 2. So in some sense, singularity helps. If you have a singular kernel, much better than bounded kernel. You get global smooth solution independent of any constraint on the initial conditions. And in fact, as t tends to infinity, you approach a limiting traveling profile, which I would call flocking profile. And this is not to be taken lightly here, because if you just pretend that the density here equals to 1, just pretend that there is no density. Now we are coming to an extremely important point. Just assume that the density is 1. So this equation amounts just to the fractional Burger's equation. And it was first observed by Chang Gui and Kiselev and their co-authors in a beautiful paper that when alpha is between 0 and 1, then the solution breaks down when the density is 1. But when the density is not 1 and it's being transported, this is the density of the crowd, the solution does not break down, which is quite dramatic difference. So there were several papers and several works in these directions. So something is going on here. The very fact that if I will now remove the density and I will get finite time breakdown, and I put the density and there is no finite time breakdown, is important. So the density plays an important role here. And then what do we know about the two-dimensional case? In the two-dimensional case, it turns out that also in the case of bounded communication kernel, we need to bound the divergence from below, and we need to know something about the spectral gap. And under these conditions, you get global smooth solution, and this is it. And there is nothing known about more than 2 space dimensions. It took a long time. I mean, many other works, I'm just compressing it, just to give you a sense that the question of existence is problematic. It's by itself an important question. But once we know that there is a global smooth solution, then we know that the large time behavior smooth solution will flow. Okay, so now I'm running a little bit out of time. I wanted to tell you about this issue of critical threshold, which was actually pleasing to me. There's a long history for this critical threshold. I started working on these aspects only in the 90s without knowing anything about flocking. And we worked on this kind of an equation, and you can see here this kind of convolution model, and we get this notion of critical threshold and regularity. So this was in the 90s, and later on with Chang Hui in his thesis, this was improved to find out what is the threshold, and there was some sort of a breakdown between when do you get global smooth solution, when you get finite time breakdown, and finally, I'm jumping, and finally, the work together with this, with Carrillo and Choi, we were able to show precisely the finite time breakdown and the critical threshold. And maybe let me do one computation. I still have a few minutes. Let me do one computation to show you there's a lot of delicate aspects to these questions of regularity and behavior, and I'm just giving you the information from above. So let's study this equation. So here's the equation, right? So here's our mass equation, and here's our alignment equation, right? We transport in the alignment. Here's the communication kernel, depending on the distance, my velocity, my neighbors, the density, and we want to know, do we have global smooth solution? So yeah, do we have global smooth solution? So let's see. We take the first equation and we write it as rho t equals minus rho ux. It's obvious. Then we take the second equation and we write it in a commutator form. The first equation tells us that here on the right-hand side we get a convolution with the mass minus u times convolution with the density. We differentiate this equation. We always do this when we look at the Burgers type transport. We differentiate and let prime denote differentiation along the particle path. When we differentiate, we get, of course, the derivative of u, which I will call by d. Reasonable. So let's see what we get. We get, of course, the transport of this term, but when you differentiate, you get another term because of nonlinearity, which involves ux squared. This is one of the terms, and here's d squared. And this term, d squared, is responsible for all the blow-up in all the scalar conservation laws we always get at, namely the quadratic nonlinearity without anything on the right-hand side will lead to finite time breakdown. This is the appearance of shock discontinuities. However, on the right-hand side, we get an interesting term. Let's do it. First of all, we have to differentiate these parentheses. Here they are. Then we have to differentiate this parentheses. Here it is. And finally, we have to differentiate the ux. Okay, we just did it. However, when we look at the term rho ux, we remember that rho ux is minus rho t. So here it is. So actually, we convolve minus phi with rho t. And now you see that what we have here is in fact the time derivative of phi convolution rho and the x derivative of phi convolution rho. So these two terms is nothing but the transport of phi convolution rho. So we bring them together and we get the transport of phi convolution rho minus d times phi convolution rho. And like magic, everything fits. And we get, instead of a Riccati equation, we get a Riccati equation for d plus phi convolution rho balanced by minus d times d plus phi convolution rho. And this equation does not always blow up. In particular, if this parenthesis is positive initially, it will stay positive, and therefore you get global smooth solution. And this is the reason that you get the critical threshold, and it's an if and only if condition. In fact, this beautiful argument requires to introduce the magic quantity called, if this is d, so this quantity will be called E. And there's a lot of mileage that was taken on the property of the quantity E. And it works not only with bounded convolutions, but actually with general operators, singular or not. So there's a lot of work that was done with Roman Schweitkoy in one approach and different approach by Chang Hui, but they all take this advantage from this magic quantity E, which is still to be explored. It's what can be done with the quantity E is not clear, because this is a magic quantity. Due to time, I will rush away and I will just tell you that what it follows, that because the quantity E remains bounded, it turns out that the density also is bounded away from vacuum. So there's a delicate argument that I have to skip due to lack of time. And it follows that the density is bounded from above and below. At the time, I did not understand the importance. Okay, so you have to prove certain things. You know, you prove the estimate, you don't see the big picture, but over time, things crystallize. And now it is clear that the most important thing is that you stay away from vacuum. vacuum is the critical element. All the other estimates, which are extremely delicate, are really not important. There's only one thing which is important to show that the density, you stay bounded away from vacuum. Why is this so important? It also took some time to understand. I'm telling you the story. I'm telling you.
Is that the same as in your first lecture, the connectedness of everything?
Exactly. That's exactly the same. So connectivity is the key element, and staying away from vacuum is the key element. And the whole thing here is about one thing and one thing only: information. That's it. It took some time to. That's what I wanted to say. So you have to work out with the details, but once you have all the trees, you don't see the forest. And the forest is that you want to stay away from vacuum. And that's what happens here. So the density is bounded from above and below. There is a lot of stuff here. Let me skip that, because it's also technically very delicate and very important. And everything is in order to prove that the one-dimensional model has a global smooth solution. Once we know it's a global smooth solution, we know that it will flock. Okay. And the same story goes in this two-dimensional case. For example, when you take the two-dimensional system and you start to differentiate and you use this argument that I show you about the magic quantity of E, and you try to balance the various terms. So this is a work with a former student. And you get now the trace of a square of a matrix, and you are missing certain terms. In order to fit everything, it turns out that you have to take into account also the difference of the eigenvalues, and then it fits. So the same argument works, namely you find this magic quantity E, which is the divergence plus phi convolution rho. You bound it, you get global smooth solution under a critical threshold. So this whole long exercise of many people, not just me of course, many people trying to understand the large time behavior and first of all the existence, show that you are able to prove the boundedness of the density, and from there you go further. Okay. And finally, in the last 15 minutes that I'm left, unless you have questions, I'm very unhappy, because so far I did not solve anything which is relevant. And the relevant question is, what about short-range interactions? I really do not know anything about that. And therefore, 2 years ago, I decided, with many postdocs and students, to try to attack this problem. I don't have a final answer on that, but I will give you 5 different answers. 5 different answers to the question is, what is the large time behavior for phaseful models which involve short-range interactions? And it turns out that as we penetrated this question, we had to revise the whole concept of what is collective dynamics. Okay. So this is the question, what about the more realistic short-range interactions? So my problem is that the diameter R0, if you remember my ball, I assume that my ball of interaction is much, much smaller than the diameter of the group. I do not discuss everything with everybody else. Okay, so answer number 1. Before we start, remember the key estimate couldn't be simpler, right? The rate of change of the fluctuation equals the entropy, which is exactly the fluctuation, but weighted by the communication kernel. So we just want to pull it out, but if you'll pull it out carelessly, then you'll get 0 and nothing will be happen there. So why this entropy is so important, and what does it mean? So here's result number 1. I will not get into the details, but I will just tell you how it works. And this is with Javier Morales and Jan Pesek. And it says, statement number 1, assume that lambda, which is the intensity of the alignment, is large enough. How large one can quantify. Then, if you start with an ensemble which is connected, and the density is different from 0, it will stay connected, and then you will get into flocking state. So basically, this is what's going on here. Instead of reading the words, it essentially means that every point to any other point in the audience or in the crowd, basically there are circles of propagation of information, and once you start with this scenario, it will never break down. That's basically what's going on. And the reason is that you need lambda to be large enough. So the flow will not change the crowd too much. That's basically the first statement. How do we show that? We basically show that the entropy bounds from below by the fluctuation, if lambda is large enough. So this was the first indication, okay, that if you have strong alignment, it follows that you get convergence to a flock. The second part talks about regular kernel with lambda which is reasonable. I will just say the statement. So here we have the communication kernel. It's compactly supported. So here's a general statement. And this is my result, and it says the following. Let's assume that the integral of our kernel is 1, and we are talking about a torus. If the integral is 1, it's essentially saying that the zeros Fourier coefficient is 1, properly normalized. The zeros Fourier coefficient is 1. Hence, all the other discrete Fourier coefficients are less than 1. Let's look at the difference between 1 and the other Fourier coefficients. It's a positive quantity. If the variation of the density is inside this positive spectral gap, then you get global smooth solution. So this was the first, the second attack on this question of flocking for short-range interactions, and it's connected to what I mentioned about this heterophilous dynamics, and it is essentially a probabilistic statement because I already assumed that I move from the discrete to the continuum. Notice all these results apply only to the continuum description. Okay, we now come to the third attack, which is a recent work with Roman Schweitko, which is, to my humble opinion, is the most important statement. And the idea is, and I will tell you how it comes into life, is to introduce a new paradigm. And the new paradigm says the following. All these models about self-organized dynamics, they are deficient. Why they are deficient? Because the new paradigm says the following. The interaction between agents depends not on their distance, and I think that the interaction in social hydrodynamics does not depend on the distance. We are not particles, but it depends on how crowded is the intermediate region of communication. So it's the first time that I introduce the word communication in a specific way. Namely, if you have two pedestrians, just think of from your own life, and you would like to anticipate where they will go, it's really a function of how crowded is the region between these two pedestrians. It's important how crowded is the region. And so is the communication between birds. And in all these aspects of social hydrodynamics, living agents, you really take into account the density. It's not just a function. In physics, you create a field, and then this field is basically influence all the other particles. In social hydrodynamics, you have sensors and you probe the environment. That's a fundamentally different behavior. Of course, all of this I'm explaining to you a posteriori, because the reason it worked out is as follows. So if I'm here and there's another typical agent there, I create this kind of bubble, and this is the region of interference, and I take into account the topological distance, which has to do with the total mass. This is the integral of the density properly normalized inside this distance. And then I would like to see that the more crowded the region is, of course, the communication will go down. It's very reasonable. So that's what we do. We look at phi, not of the distance between x minus y, but as a function of 1 over this topological distance. So the more crowded it is, the communication will go down, and if it's empty, the communication will go up. So here it is. We have a communication kernel which is symmetric. First of all, I take into account my ball. So this is a finite range. And then within this ball, I pay attention where there is air and where this is crowded. And if it's crowded, then there is less communication. And if it's not crowded, the communication will increase. So this is the new paradigm that we introduced here. But it's not a new paradigm. And again, I'm running out of time, but you remember I told you about experiments. So there is a very famous experiment that lasted for several years of a group of physicists led by Parisi about birds. It's called the Star Flag Project. If you keyed in the word star flag, you will find out that showed that birds do not communicate based on the distance, but they communicate by finitely many closest neighbors to them. And that's exactly what this quantity measures. It measures the immediate neighbors, finitely many, the number of them. And then there is another experiment about pedestrians, which shows that actually humans do react to the crowdedness and not just to the distance. And based on that, we look at our model. Now we have this phi with topological distance. This is a communication protocol. It's highly non-trivial because it's singular. One has, again, to do a lot of work. But after a lot of work, the answer comes if the density is bounded by 1 over t, and we have this short-range interaction, then it follows that there is flocking, and the idea is to have this kind of, here is the picture, I'm here and somebody else is there, and we have a communication, and these balls somehow always persist, because once the density go down, then we communicate in an urgent manner. So that's basically the technical aspect of short-range interaction. Notice what I put in red. I have to assume that the density is greater than 1 over t. I do not want to have vacuum, so this is an assumption. In fact, if you allow me to put here square root, then I can prove everything that you want. But this is too strong an assumption, so one has to know what is really going on here. And indeed, we were able to show that in the one-dimensional case, and that's what promoted this whole study, in the one-dimensional case, the density is bounded from below, and there is a global regularity, and the reason is because of this magic quantity E. And here's the magic quantity. It is not a convolution, nevertheless it survives, and there is some further magic there which actually promoted us to introduce this topological distance. So this is a new paradigm, and when I think about it today, I think that this is the way to go, but of course the problem is completely open in more than one space dimension. This paradigm is so important that brings me to another result with a postdoc, Ruwen Shu. I just tried to convince you that the discrete case is hopeless because Kant said so and blah, blah, blah. In fact, it is not. So here's another result. So let's go back to the discrete case, which was completely hopeless, but with the topological distance. And the topological distance basically measures how many agents, counts how many agents are between me and Bobby. And if there are more agents, then of course our communication will go down and vice versa. So let's cut off. If the density will increase certain threshold, I will stop communicating, period. That's it. So this will be sort of the discrete version for short-range communication. And in the discrete case, here's the theorem that there is an alignment with topological cutoff which lead to communication. And this is truly a non-trivial result. Because it's discrete, it has to do with combinatorial counting of who communicates with whom. I mean, this is not just by energy estimate. I mean, the discrete case with short-range interaction is way too complicated. And I must say, I even tried to beat this theta to the 9s that originally was derived by Ruwen, but apparently I was unable to. So I don't know if this is optimal, but something along these lines. So this is attack number 4. Attack number 5 on short-range interaction falls under the category of games. So what is a game? So let's take the following scenario. Suppose that we have not just one crowd, but we have several crowds, different crowds, which I will identify by the Greek sub-indices alpha and beta and so forth. Now, what distinguishes one crowd from the other crowd? Well, the way they interact. So suppose we have many agents, which is actually much more realistic. We have many agents, and each agent interacts with other agents with a different protocols. Why should we have the same protocol? So if you go to the crowd dynamics, large crowd dynamics, we have a crowd number alpha interacts with crowd beta, including its own, and what's distinguished them is these protocols, the phi alpha betas. Okay? And now we'd like to see what is the large time behavior. So why do I mention this? Why is it games and why is it short range? So here's a statement. If all the phi alpha beta will be the same, this is everything we've done before. If all the phi alpha beta will be just the multiple of Dirac masses, then you get different crowds and everyone plays by himself or by itself. Now we have different crowds and they communicate or not. Some of them communicate, some of them do not communicate. This phi alpha beta may be 0. And so this is the multi-species behavior, and here are the agents and here are the species. What will happen in this kind of very noisy system? Well, let's assume that phi alpha beta, these are the lower bounds, which are greater or equal to 0. So some of the species discuss with the neighbors and some of them do not, and the statement is, if this matrix is connected, then you will get consensus. What does it mean it's connected? Well, here's an example. So let's take this matrix, 0, 1, 1, 0. What does it mean? Suppose there are two crowds. In my crowds, I don't pay attention to my own species, but I just care about the other guys. And the other guys, they do not care of their own species, but they just care of my guys. Eventually, you will get into consensus. The reason is because this matrix is connected, and so is this matrix. So you do not have to have a scenario where everybody talks to everybody else. It's enough to keep connectivity. And this is the main theme that we see again and again. You notice, of course, that we need to stay away from vacuum. And at this stage, it's clear that the only thing that matters is to stay away from vacuum, keep talking. Eventually, you will get into consensus. Even me and Ron will get into consensus when we keep talking about politics. So we keep talking. So that's basically where we stand as far as the short-range interaction. And that's the reason it's so important to my taste, that short-range interaction is a completely new, but we seem to gather this basic understanding that you have to have connectivity propagating, and we try to understand how to prove it analytically. And finally, I would like to conclude. Remember, I started with external potential. So this is just an alignment. What about the external potential? We add the external potential now. And there is a series of works because we have to take into account everything else. And now we get much more interesting dynamics, because another thing that bothers me, not only that the models are not realistic, now they are more realistic, we just get that everything gets on the same point. This is it. That's the main message. No. It turns out that actually when you flock, you get much more interesting scenario. So here's an example. When you take the potential to be quadratic, now you do not get into a point, and let me show you what you should get. And this is the simplest case. And you can see now how the flock turns around, and eventually it will go in periodic orbit. And this is the simplest case. If you give me with the potential to have several minima, then it will become considerably more complicated. So everything we study so far with short range will have to come on top of what's going on here. So this is exactly where we stand now. And at this point, I think, yeah, so what you get here is not only that you get alignment of velocities, but you get alignment of the location, you get concentration of locations. Of course, this is a very special case. This is the case that you get just attraction. The real case is what I started in page number 1, namely when you get repulsion and attraction, and that's left for the coming years. Thank you very much.
Dominated by something you wish to obtain, right? Or is it more the question, I want to fully understand when there is flocking in order to better understand all these other scenarios which you might observe in life?
Okay. Okay, so after being so critical, I should lower my criticism a little bit. You know, I see it as a journey. In this journey, and I started this statement, I would like to understand what are the important features and how the short-range communication affect the global patterns. And here are the things I learned. And now I don't impose anything a priori. It is clear that you get this, well, I would like to look at the hydrodynamic description or social hydrodynamics. And I know now more about this communication protocol, and I know that the heart of matter is that this communication protocol should be short range. Whether it's topological, whether it's geometrical, whether other people would like to bring more to the table, fine. But I know that it's important to distinguish between the short range and long range. This is one thing. I personally believe that this topological offer a very interesting path, and I do not know where it will go. That's number one. Number two, I realize that one has to address, in addition to the alignment, which is just one component, additional terms which have to do with essentially repulsion and attraction. And now the repulsion and attraction bring you a scenario which is far from the usual convergence to a Dirac mass. These are the simplistic cases. And I think at this stage we have a pretty rich framework which goes back to slide number 1, namely anticipation. If you remember, when I talked about anticipation, I said, well, first of all, you get alignment and you get an interaction which is a matrix interaction. We still have to do that. I mean, so there's a lot of stuff to be done here. This is an uncharted territory that I'm pushing now for the last 5 years forward.
Maybe a second question. If you forget this right-hand side, which is the source of all your concerns, really, if you only have the first side, it's easy to understand that when classical solutions cease to exist. So people jump to weak solutions. They try to develop other notions of solutions which are much less restrictive.
Correct.
As opposed to sticking to a point-wise interpretation.
This is fantastic. I'll address that because this is one of my to-do list. I have a long to-do list. Develop a theory of weak solutions for these alignment models for supercritical data, initial data. Yeah. So there are 2 ways to go. The canonical way along the lines of conservation laws and fluctuation and total variation. The other way about minimization properties of the entropy. You try really to minimize certain cost function, which is built into the system. But I'm now after the short range.
When you go even back.
That's a very deep question. I agree with you. Sorry.
But even if you go back to the kinetic level, to it there, in the kinetic level, you jump to moments. Because moments is again something you understand points. That means you test your equations with only a few guys, right? And then you need to close. But what if you go to weak formulations already there?
I think that for kinetic formulation, do you know that? I think kinetic formulation is global smooth. Yeah, it has global smooth solution.
We're taking a moment, so it's not, the nonlinearity really happens.
Yeah.
But the moments is testing with a very limited ensemble.
So in X-free variable, everything is smooth, but when you integrate, then there is when these kind of...
There's another notion here. Yeah, in the kinetic level, there is a global smooth solution, right? Because it's linear. It's not Boltzmann that there is a gain and loss. You notice that, I mean, this whole discussion, I didn't say even once the word entropy, which another thing which bothers me, because in the notion of communication and PDEs, you have to talk about the word entropy. So where is the entropy here?
That's what I meant with the weak.
Well, so it's also something which is not clear to me because it does not satisfy the usual entropy inequality. There is an entropy inequality here. It's not the usual one, still to be explored. I mean, there are many directions that have to be done here. On the one hand, you can develop the mathematical theory, but you have to stay truthful to what is on the ground. So.
More curiosity, you were mentioning that, like, when you were passing the limit, one key assumption where all the agents were indistinguishable. That's something being done with maybe agents that have some ranking or importance.
In this context, yes.
Question.
What?
The leader question.
Yes, no, but this is even before the leader questions. I mean, whether they're indistinguishable. So the answer is yes, and the person who did that is specifically is Pierre de Gon, and in some sense, again, you know, God is in the details, so I don't want to simplify what he says because it's a very deep work. It's actually recent work. It's exactly about this question, and it is about the fact that you have to distinguish between different agents because different agents, so this goes back to a fundamental property. It's another one of those things that we sacrifice for the sake of these models. We say, well, we have agents, we have birds, we have humans, but somehow they're all the same, which is of course not true, right? So I already mentioned, if you have opinions, you also have convictions, and the convictions vary from person to person. If you have birds, they have different weight. And the weight is important. You say, okay, so this is like the mass. Okay, so what about the age? In fact, what you find out that different agents have different kind of energy consumption, because particles do not consume energy, but agents do. You do not have your conservation of energy. So once you put this into the system, you have to see that you have to take the different particles, and they are distinguishable. So once you put it into the system, it becomes complicated, because there is a lot of combinatorial aspect in the passage to the limit. So the key word is that I can think of right now from the top of my head is Degon, Pierre Degon.
Again, thank you very much.